All right. Okay, so we were talking about the mole-to-mole conversion using a balanced equation. So I think we were looking at this problem right here. Oh, let me see. Holly said I have a couple questions. Then about the test, can we go over after the lesson? Yeah, actually, why don't we just do it now? Holly, if you just want to go off the mic, if that's possible, that might be easier. Well, are these questions about the lecture material? Because I think we're doing a review. Aren't we doing a review in a few days? That's kind of when I wanted to wait for everything. I kind of want to stay on the schedule. If your questions are just about the format, I'm okay in answering that. But if you have questions about the actual lecture material, I kind of wanted to stay on our schedule here. Because we were going to do the review on Thursday. It's from the previous test. Oh, the previous test. Yeah, why don't we wait until after class? Yeah. On the previous test stuff. Yeah, okay. Okay, so this was mole-to-mole conversions. So what we're doing is using the balanced equation to figure out our mole-to-mole. So I have, a 1 here, a 1 here, and a 2 here. Okay, so I think the problem what we did is B, determine the corresponding mass of the water produced in the reaction. So I don't think we did A. All right, so assuming calculate the mass, determine the corresponding mass. So it was 10, calculate the mass of ammonium nitrate that must be heated in order to produce. So let's do 10 grams of water here. So how many grams of the ammonium nitrate is needed if we produce 10 grams of water? All right. So what we start with is the grams of our ammonium nitrate. I'm sorry, grams of water. So we start with grams of water. All right, and then we got to convert it to moles of water. So water weighs 18.01 grams. That's the 1 mole of water. And then the mole-to-mole conversion. So there's 2 moles of water for 1 mole of the ammonium nitrate. And then we now need the mass of ammonium nitrate. So 1 mole of ammonium nitrate is, someone has a calculator, so let me grab this real quick. So it's 14 plus 4 plus another 14 plus 2, so 80. You get about 80 grams per mole. So 10 times 80 divided by 2. So 22.2. 22.2. Okay. So just to kind of remind you, the answers aren't there. Just to remind you how to do it. So like this chart right here, you have your mass of your reactant, so mass of your starting material, convert it to moles, and then use the mole-to-mole conversion in order to get the moles of what you want, and then the mass. So if you remember this chart that I did in class several times, this is grams of A. And then you remember we did the number of molecules of A, and then you get moles of B, you get grams of B, and then molecules of B. All right, that's kind of what this is going here. So we started here with 10 grams of water, and we're going here to 10 grams of ammonium nitrate. This time your mole-to-mole conversion is the balanced equation. You're using the balanced equation. Oh, that's a cube. Okay? So that is the new part. Any questions on that? Why don't we do a practice problem? Maybe that's why I have this here. Let's think. Let's see. Let me think real quick. How many grams of chlorine gas is required to react with sodium metal react with, let's put 20 grams of sodium metal. How many grams of chlorine gas is required to react with 20 grams of sodium metal? All right, so kind of a review for the exam on Wednesday. I'm not going to tell you what the chemical equation is. At this point, you should be able to figure out how to write that chemical equation and how to balance it. Okay, so I give you chlorine gas. You should know the structure of chlorine gas. You should know what sodium metal is. When you react them, you should be able to figure out what the product is. All right, it's one of. I'll give you a hint. It's a redox reaction. Okay. So I will let you work on that first. All right, I'll give you a few minutes to work on that. Okay, so let's go over this. So how many grams of chlorine gas is required to react with sodium metal? So sodium metal, that's sodium. Remember, it's a solid if it's a metal. If you put a solid, that's fine. If you don't put a solid, that's fine. And then chlorine gas, remember, chlorine is a diatomic molecule. So it's sodium plus Cl2, and then your product, which is sodium chloride, is NaCl. And then in order to balance it, there's got to be a 2 there and a 2 there. So this would be the correct equation and balanced correctly. So you first have to get this. Obviously, if you can't get this, then your mole-to-mole ratios would be wrong. Now, on the exam, I just want to let you know, what I usually do is if I do a problem like this, I first have you come and you check the balance equation for me first, just to make sure that you have the correct balance equation, because I don't want you to do all the math having the wrong values here. But since we're doing everything online, it might be a little different. All right. However, this is something that you should know at this point, or at least close to it, based on the fact that we're going to have the exam on this. So, any questions on how I wrote the equation, and understanding the chemical equation, and the balancing and all that? Okay. So we start with 20 grams of sodium. All right, sodium I think is 23 grams. Does that sound right? I don't have a table. Just grab this real quick. Sodium is 23. Yeah, let's say 23 grams. Sodium, that's for 1 mole. Sodium. All right, and we're going from sodium to chlorine. So it's basically saying how many grams of this do I need if I start with 20 grams of this in order to have a complete reaction. All right, so it's a 2-to-1 ratio. So sodium, 2 moles of sodium is on the bottom, and 1 mole of chlorine is on the top. And then 1 mole of Cl2 weighs, I believe it's 71. Go and check, 35.5 plus times 2. 71 grams is the molecular mass of Cl2. All right, does this look right to everybody? So 20 times 71 equals, divided by 23, divided by 2. Let's see, let's do 3 sig figs. So I have 30.9 grams of Cl2. Is that about what you guys get? On the same page. Yep, okay. All he says, yep. I'll have to say yes and then yep. Yes up. That's funny. Okay, good. Any questions? All right, because this chapter, obviously are layers on top of each other. You got to understand this before we get to the next section, and then so forth and so on. Make sure everyone's got this. Okay, good. If there's no questions. Okay. Next section is limiting reagents. Something called a limiting reagent. Let's see what kind of, I don't really give the example I give. So on the videos, the example I give is about making grilled cheeses or cheese sandwiches. All right. So let's talk about what a limiting reagent is using this example. Let's say you're going to make a grilled cheese. All right. You're going to use bread. All right. BD will be our atomic symbol for bread, and we're going to use cheese. All right. So in order to make a cheese sandwich, we always need 2 slices of bread. All right. And your final product is BD2CH. It's your cheese sandwich. All right. So 2 slices of bread for every 1 slice of cheese, and you get this as your final compound. Okay. Our cheese sandwich. Okay. What a limiting reagent is let's say you have 6 slices of bread. Let's just put 6 slices of bread here. All right. And you have, let's say, we'll do it in yellow, 2 slices of cheese. All right. How many cheese sandwiches are you able to make? What's the maximum number of cheese sandwiches that you can make? 2. Exactly. I can only make 2 cheese sandwiches because this will make a sandwich and this will make a sandwich. Right? Just because I have 6 slices of bread doesn't mean I get 6 cheese sandwiches. All right? And in this case, the amount of sandwich is limited based on my cheese. I have less moles of cheese than I do of bread. So I can only make 2 cheese sandwiches. So 2 BD2CHs. Again, moles. This is based on moles. Okay? So I have this many slices of bread left over. That's my excess reagent. That's how much is left over. So the number of cheese sandwiches is limited to whichever one of these is in the least amount. All right? Does that make sense? If I have like 6 slices of cheese, and let's say I have 4 slices of bread, how many cheese sandwiches am I able to make? What do you guys think? What's the maximum number of cheese sandwiches I can make? If I have 4 slices of bread. Okay, so Kimberly says 4, 22, and now 20, and now 2. That's all right. Yes, so again, I can only make 2 cheese sandwiches. Because remember, there's 2 slices or 2 moles of bread for every slice of cheese. All right, so if I have 4 slices of bread and 6 cheeses, I'll put them in circles, 1, 2, 3, 4, 5, 6. This is a cheese sandwich, and this is a cheese sandwich. So 2, and then I have 4 slices of cheese left over. So now my cheese is in excess. And the amount of cheese sandwiches is limited based on how much bread I have formed. And that's basically what the limiting reagent is. All right. In the previous example, in this example, we are trying to get exact amount of each. All right. For every 20 grams of this, I need to add exactly 30.9 grams of this, and I will have a complete reaction. All right, but that doesn't always work. What if I had 40 grams of the chlorine? Okay, so if I used 40 grams of it, but still used my 20 grams, I would still only form the certain amount of sodium chloride based off of the 20 grams because in this case, my sodium is my limiting reagent. Okay, and the other, 9.1 grams of chlorine is left over. Okay, so up until now, we've been assuming we have exact amount of each, but that doesn't always happen. I might have a little bit more of one than the other. Okay, so I'm going to show you how I like to do these problems. Your book tells you a different way of doing it. I think it actually has more work. So I'm going to show you how I like to do this problem. I'm going to copy and paste this and put it into the actual program that I like to use. I don't like to use this program because the pen gets all messed up. Oh, I don't have the full thing. That's all right. Okay. All right. So in this problem, ammonia is produced by the reaction of nitrogen and hydrogen. So here I have the balanced equation. According to the equation below, determine the limiting reagent and calculate the mass of ammonia. So this is what we're looking for, the mass of this ammonia. When 35 grams of nitrogen reacts with 12.5 grams of hydrogen. Now, quick question. Can you tell which one is the limiting reagent by the mass that are given of each of them? Like, if I'm only using 12.5 grams, that, doesn't that imply that maybe hydrogen is my limiting reagent? All right, I'll tell you the answer is no. You can't assume that because it's the number of moles that we're looking at. Plus, notice, we need 3 times the amount of hydrogen in order to react with a mole of nitrogen. So these have to be converted to moles before we can assume what is our limiting reagent. Okay? So the way that I do these is I just basically do 2 problems like how we did in the previous examples. I take my 35.0 grams of nitrogen and figure out how much ammonia is produced out of that. And then I take the 12.5 grams of hydrogen and do the same thing. I figure out how much ammonia is formed. Whichever one gives me the least amount, that's what the answer is. Okay, so I'll show you. Again, I do it a little differently than what the book does because I think this way saves you time, and I think that you don't have to think as much either. So you're going to take your 35 grams of nitrogen, and you're going to convert it to grams of ammonia. So nitrogen is 28 grams. It's the 1 mole of nitrogen. And 1 mole of nitrogen gives me 2 moles of ammonia. I'm sorry, of hydrogen. Hey, Garrett, you're about an hour early for class. I'm in my other class. Sorry about that. Okay, sorry, I have something wrong here. Nitrogen, this should be ammonia, NH3. All right, and then 1 mole of ammonia weighs 17 grams. Okay, so what this is going to do is it's going to, let's see, sorry, I thought it was. All right. So what it's going to do is it's going to figure out how many grams of ammonia this amount of nitrogen makes. It's like doing the cheese sandwich. If I have 4 slices of bread, that means I can form 2 slices of cheese. That's kind of what I'm doing here in this equation. All right, so 35 times 2 times 17 divided by 28. So you get 42.5 grams. All right, so 35 grams of nitrogen forms 42.5 grams of ammonia. All right, now we're going to do the same thing with hydrogen. So 12.5 grams of hydrogen, and we're going to do the same thing, but we're going to do it with hydrogen. So hydrogen weighs 2.02 grams is to 1 mole of H2, and then 3 moles of H2 is to 2 moles of ammonia, and then the mass of ammonia is 17 grams per mole. Does everybody understand my equation? Make sure you understand where all the numbers are coming from. So here I get 70.1 grams of ammonia. All right, Kim says yes. So that's good. All right. So 35 grams of nitrogen forms 42.5 grams of ammonia. 12.5 grams of hydrogen produces 70.1 grams of ammonia. So therefore, the limiting reagent is the nitrogen, because that gives me the least amount of product based on my hydrogen and our nitrogen. All right, so nitrogen is limiting because I only can get 42.5 grams of ammonia. That means the answer here, when it says calculate the mass of ammonia, I can only get 42.5 grams of ammonia. I can't make more than however much, whichever one is my limiting reagent. So these numbers are telling me since the nitrogen produces the least amount of ammonia, I can only get 42.5 grams of ammonia out of it. All right, does that make sense? So that means all 35 grams of this has been consumed. All of this has been all consumed, and I formed 42.5 grams of the ammonia, because the 12.5 grams of hydrogen can produce up to 70.1 grams. All right, again, it's like saying our cheese sandwich. If I have 4 slices of cheese, all right, but I have like 4 slices of bread, but 6 slices of cheese, all right, I can only form that amount of it. This amount is in excess. Okay, so what I'm basically doing is I'm taking the values and finding out how much maximum I can form of each of them. Whichever one is the smallest amount, that's the maximum I can produce. I can't produce more than that. If 35 grams only produces 42.5, once I hit that 42.5 of ammonia, I don't have any more of the nitrogen left. It's been completely consumed. Okay? Does that make sense to everybody? Okay, good. Good. So here's a quick question. How much hydrogen has been used? Out of this 12.5 grams, since all of it has not been consumed, only a portion of it has been consumed, you can quickly figure out how much hydrogen was used. How do you think you do that? And remember, it's something called the conservation of mass, which we learned about, meaning that matter isn't created or destroyed. It's just used up. So can someone quickly tell me how much hydrogen was used based off of that? If not, I can go over it, but I'm going to see if someone is able to get that. How much hydrogen is used? You don't have to do a calculation like this. You can do simple arithmetic. So here, I'll give you a hint. Out of this 42.5 grams, how much of it is the nitrogen? How much of this 42.5 grams is the nitrogen? The answer is all of it, right? Because this is my limiting reagent, so all of this has been consumed. So out of this 42.5, 35 grams of it is the nitrogen. Therefore, the remaining amount has to be the hydrogen. So 42.5 minus exactly 35. So out of this 12.5, 7.5 of it is the hydrogen. That's how much hydrogen was used in the reaction. So the remainder amount is the amount in excess when it says which is the excess amount and how much is left over. So now it's 12.5 minus my 7.5, which is what, 5? Is that 5 grams? 5 grams of the hydrogen is left over. Am I recording this? I don't know if I'm recording this. Oh, yes, I am. Good. Okay, so does that make sense? Does that make sense to everybody? Let's see how I got all that. Okay, so first, what I do is I take both numbers and I figure out how much product it's formed, or whatever my question is asking for. Whichever one is the lower of the two, that's the answer, and whichever reagent gave the lowest one is my limiting reagent. And then you can go ahead and backtrack and figure out how much is in excess based off of knowing that all of this is consumed. And if this is our total amount, I subtract that out, and then I can figure out how much of this was used based off of whatever's left over. Okay? All right. So let's do another problem, just to make sure that you guys got it. Let's clear this. Okay. Let me write an equation here. I'll just write it out so you guys don't have to worry about it. You know what? Let's use that sodium one again. Okay. If 10 grams of sodium reacts with 10 grams of Cl2, how much NaCl is formed? All right. What is the limiting reagent and how much excess is left over? All right. I'll give you guys a few minutes to work on that. Okay, so start with 10 grams of the sodium. Sodium is 23 grams per mole. And it's a 2-to-2 ratio, which is basically 1-to-1. So if you left this out, you'd still get the right answer, but that's not a good strategy to let that out. You should still put it there just in case. So 23 plus 35.5, 58.5 grams. Hold on 1 second, guys. Going upstairs. He's doing weights. I don't want you in there doing weights with him. Okay? I let him do weights for his arms. I don't want you to hurt yourself. Okay. Okay, you can go. Don't hurt yourself. I gotta continue. Alright, sorry about that. Kids are done with whatever their assignment is. Alright, so I get 25.4 grams here of sodium chloride. And then we do the same thing for chlorine. I'm just going to put the numbers. I don't want to keep writing all the... so this is 1, this is 71, and then this is a 1-to-2, and then 58.5. 58.5. So 10 times 2 times 58.5. Yeah. 16.5 grams. Does that make sense? Everybody gets? So you form 16.5 grams of sodium chloride because it's the lower of the two. That means that means my chlorine is my limiting reagent. That means my excess reagent is sodium. And then how much sodium is left over? What do you guys get? Yep. Yeah, I was going to put 3.5, just because of how it came out. You obviously used more sig figs than I did. I get 3.50. But yep, exactly. You just take the 10 grams of sodium, which is how much I started with, and you're subtracting the 16.5. No, I'm sorry. Yeah, so you take that in order to get 6.5. All right. And then you take that and subtract that from the 10. Because I used 6.5 grams of sodium. So the 3.5 is what's left over. That's how much sodium is left over. Okay? Make sense? Questions on that? All right, the next part, okay, good. The next part, I'll just talk about it rather than going back, is what's called percent yield, because I want to use this as an example. Percent yield. Actually, I'll tell you what. Let's just go to it. All right. What the percent yield does is it tells you, it's basically a percentage to tell you how much of your final product did you actually get. Now, the last example says that we should have gotten 16.5 grams of my compound. Okay? This is what's called my theoretical yield. In theory, this is how much I should get. Okay? So that is my theoretical yield. That's based off of calculations. It's based off of the maximum amount of compound I should actually form. That's the theoretical yield. The actual yield is what do you actually get in the laboratory. In a perfect world, I would get exactly 16.5 grams, but that does not happen because you might spill the solution, some of the compound might stick on a container when you wash it off. So there's lots of reasons as to why you don't actually get the actual amount. Okay, so in theory, I should get that. Maybe I actually only got 15.3 grams. So after I did a reaction, I calculated I should get the 16.5, but after I isolated the sodium chloride and I weighed it, I actually only weighed 15.3 grams of the 16.5 grams. So in order to find a percent yield, you just take that 15.3 and you divide it by the 16.5 and you multiply it by 100. And that's your percent yield. That's how much you actually isolated in real life. Okay, so it gives me 92.7%. So this basically tells a reader or somebody that you've isolated 92.7% of the actual compound. All right, and that's basically what a percent yield does. It takes what you should get in theory based off of your calculations. This is based off the calculation. This is what actually happens in lab. When you actually do a lab, again, you might not get exactly how much you should get. Usually, you don't. It's very rare in order to get 100% yield. Because again, you might spill a little. Maybe that the balance that you used initially in order to weigh stuff out wasn't calibrated properly, or it wasn't zeroed out properly. There's lots of different reasons why you don't actually get it. But mostly, it's very hard to actually isolate 100% of every single molecule that you're doing a reaction on. So that's basically what the percent yield is. Okay, so any questions on the percent yield or limiting reagents? Okay. All right, so here is another problem. So aspirin, which is also called acetylsalicylic acid, say that 10 times fast. I know someone right now is doing it. Is the most common used pain reliever in the world. It is produced from reacting salicylic acid with acetic anhydride. Here's the equation. Notice it is not balanced. This is not a balanced equation. I don't think so. That's not balanced. In a certain aspirin, actually, no, it probably is balanced. 9, 10, 11. Yeah, it is actually balanced. In a certain aspirin synthesis, 104 grams of salicylic acid, all right, which is, in a certain aspirin synthesis, salicylic acid, which is this one right here, and 77.47 grams of acetic hydride combined. Calculate the percent yield of reaction if 105.6 grams of aspirin is produced. So they isolated 105.6 grams of the aspirin. So they want you to figure out what the percent yield is. Okay, so I will let you guys work on this for a little bit so we get some more practice. All right, what I'm going to do is copy and paste this over to the next slide. Also, let me know when you guys are done. Okay, so you're going to start with 104.8 of this and 77.4 grams of the acetic anhydride. So this is the actual yield. So this amount that is produced, that's what your actual amount is. So what we have to do is figure out the theoretical amount and then compare the two. All right, so we got 100, and we also have to figure out the limiting reagent first. We have to figure out how much product is formed. So it's kind of a combination of everything. That's why I kind of liked it. So it's 104.8 grams of the salicylic acid. I'll put SA. All right. So the salicylic acid, which is this one, I have a mass of 138. Obviously, I rounded a lot. It doesn't really matter. Oh, I got my calculator back. My 8-year-old is doing his math class. It's arithmetic. It's adding 3-digit numbers like, 420 plus 132. Well, he was using my calculator to do that. And he knows not to use his calculator to do that. He's like, oh, I'm doing really well, Dad. I'm like, yeah, nice try, buddy. At least he knows how to use a calculator, I guess. All right, everything is a 1-to-1. So, I'll put 1 here of your product, which is the aspirin, and then 1 mole of the salicylic acid. And then multiplied by the mass of the acetylsalicylic acid, which is 180. 80 grams per 1 mole. And I think I get, I don't know which number it is. Is that 135.7, 136.7? What do you guys get? I can just do it real quick. I know one of them was 135 and one was 136. That was the 136. 136.8. Do 8. Round it up. Grams. Does that sound right? I'll make sure we're all on the same page. And then the other one is 77.47 grams. 1 mole is to 102. This is also a 1-to-1 times 180. If you guys can just let me know, make sure I'm getting the same numbers as you. I obviously rounded quite a bit on the oh, wait a minute. What happened? Oh, something went wrong. Oh. What's going on here? 104.85 times 136.7. 7.47. I thought one of them gave me 0.5. I mean 135. excuse me, 136.7. What do you guys got? Oh, that probably got 135. What do you guys get? Oh, I guess it doesn't matter. I mean, I got 130. Are these numbers that you guys are getting too?
So the grams for the 104 is the C7H6.
Right.
B?
Yeah.
No.
And that mass is 138. Is that right? Yeah,
Cool.
Jack says that you got the same thing.
Hold on, I'm not feeling confident. Let me just try this.
Yeah. I thought I got a different answer when I did this originally, but Jack says he gets about the same thing. 138. Yeah, that looks right. And then 9 times 12. Maybe I originally did it wrong. Plus 8 plus 64. 180. Yeah. Does everybody else confirm? If that's the case, this is our... Okay, Michael and Jack both say yes. So, all right, we got 3 confirmations. So the acetic anhydride technically is my limiting reagent. Not by much, a tiny, tiny amount. But that technically would be my theoretical yield at 136.7. So we're going to take the 105.6 and divide it by the 136.7 times 100. So, I mean, usually in reality, when you do a reaction, you do put one of them in slight excess. So I got 77.5%. When you do this reaction, you usually put one in a little bit of an excess just to make sure that you completely react it. The one usually in excess is the cheaper of the 2 reagents. So if I were to do this, actually the cheapest one is the acetic anhydride. So I would actually have that one in a little bit of excess, but that doesn't really matter right now. All that matters is that we make sure that we understand how we get these numbers and how we get that number. So is that good? Everybody okay with this? Okay. Yeah, I think I put a blank page here so that we can work on it together, but we did over there. All right, any other questions? No? Okay. All right, I think we're gonna stop right there. I don't want to get too deep into this. Also, I think Holly, was it Holly that had a question about the exam? And then we'll talk about this. I think it's tomorrow, isn't that correct? Tomorrow we'll finish chapter 11. Yeah. Yeah. Okay. So Kayla, you said no. Is that for? Are there any other questions? Is that what the answer is to? Because you like, okay. Because you like with capital letters and exclamation. Okay. Yeah, yeah, I know. Anytime that people text, it's there are times where you can take things the wrong way when they actually mean it a different way. But yeah, but I knew you. Okay, so if that's it, let's turn off.